Francisco, before we start, I will do a short introduction and then I will pass you the floor, okay? Let me just remind people again. Okay. Well, people are still joining us, but I think we can start because should not stay behind schedule. So I'm going to do an introduction and then I will pass you the floor, okay? Hello everyone. Welcome to another talk in our webinar series. Today we have the pleasure of having Dr. Francisco Förster from the Universidad de Chile. He's a professor at that same institution and has been working with astrophysical transient phenomena, image processing, pattern recognition, and data analysis. And particularly, he is one of the lead scientists of the project ALeRCE, about which he will be talking to us today. And before we start, a quick reminder that this webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, LIneA MCTI. Francisco, thank you very much for being with us today, and the floor is yours.
Thank you, Rodrigo. Thank you for the invitation, and thank you for organizing this seminar series. It's a great idea to have all the brokers present the results, and so we can have this as a legacy material for the community. So I will talk about the ALeRCE broker, what we have been doing, what we're going to do next, the challenges we're facing. And I will start with this slide with many people. You see there's a lot of people involved in ALeRCE, directly, indirectly. But what you will see is that this is a very interdisciplinary team with engineers, astronomers, computer scientists, I mean, all kinds of backgrounds. And it's also very diverse in terms of institutions in Chile. And we also have some collaborators in the US and some in Europe, in Russia as well, in Argentina. So we're trying to make this as inclusive as possible to really do the best science with the knowledge from the world experts. And you can visit the website of the project in here, alerce.science, if you want to know more. So just first as a motivation, ALeRCE is a conifer in the south of Chile and Argentina. It's kind of very similar to redwood trees in California. And so that's why we chose the name ALeRCE, but it's also the automatic learning for the rapid classification of events broker. So what we are interested in is the dynamic sky, the changes in the sky, and to be able to provide early warning system for the community, and also as well as classification and systematic classification of the alert stream. So also as motivation, you may have seen this plot by Tyson et al. 2019, where you see as a function of time the growth in collection area in telescope, mirror area, and the number of galaxies observed per year, and Moore's law, the number of transistors per CBU. And what you see is that really the number of galaxies that we observe per year does not follow the evolution, the growth in telescopes, but follows the Moore's law. So what we're seeing is an impact of Moore's law in all sciences and all society, and in particular in astronomy. And this has led to a new generation of large optical survey telescopes with large CCD cameras, and a combination of large CCD cameras with large field of view and with a large collecting area. So the two growths that we saw in the previous slide. And the product of the field of view and the collecting area is something called ETANView, and that is shown by the size of the circles here. And you see that there is a new player coming soon that is really marks a change, a quantitative and qualitative change in the way we work with survey data, which is going to be the Vera Rubin Observatory, or with its legacy survey of space and time. You can see some images, footprints of the cameras for different telescopes. This is the footprint of LSST, and this telescope will have 3 billion pixels, so it's a huge number. And today, the different brokers, I will introduce brokers later, are using as training ground the Zwicky transient facility, which has this footprint, but with a much larger pixel size. So this has pixel size of 1 arcsecond, and LSST 0.2 arcseconds. And yes, and these telescopes will be working probably in 2024, and is undergoing construction now. This is an image from the eclipse 2019. So I hope you can move this here. Yeah, so one of the motivations for monitoring the dynamic sky is, of course, discovering new objects, understanding better what we already know, find new populations that may be hidden in the data. And in the case of transients, we see, for example, in this diagram of luminosity versus characteristic timescale, that this was from 2012. There was kind of a desert of objects in this part of the diagram, and this was because we were not going deep and fast enough to discover them. And since then, we have realized that there are many events that populate this area, and there are more recent figures that show how this is being populated. But basically, what we see is that we have supernova shock breakouts, tidal disruption events, kilonova events, ultraluminous X-ray outbursts, etc. So there's a new astrophysics waiting to be discovered in here. So, and also in the case of us in Chile as a community, we are really lucky to have access to all this infrastructure, 10% of the observing time for many of the best telescopes in the world. And this is a big responsibility for us to use them efficiently. And also, well, I should change this. It's not VRO, it's Vera Rubin Observatory. The challenge of the Vera Rubin Observatory is that we will have access to 100% of the data in equal conditions as the rest of the Vera Rubin partners. So this is also different for us. Okay, so but what is this new picture that is emerging? So we will have basically 2 layers of telescopes: the survey telescopes that monitor the sky, optical from the ground, from the space, in radio, even gravitational waves. And this will be producing millions of detections of things that change every night. In the case of LSST, it will be tens of millions of objects that change in the sky. And then the challenge is, how do you decide what to follow up? with this new generation of multiplex spectrographs like MOONS, HORMOS, DESI, etc. And from new robotic telescopes and the space telescope, etc. So how do you make the right choice of what to follow, and how do you do it fast? And for this, there's a new layer that is being built, and this layer is alert brokers. So they are intermediaries between survey and follow-up telescopes, as well as the TOMs, the target observation managers, that they do the final connection with the follow-up telescope. So brokers filter the stream, classify the stream, TOMs interact directly with the follow-up telescope. So the tools that we need now are expanding. So first, we need acquisition and processing tools, something that we have been doing very well for decades now. Now we need to add the filtering and classification tools. This is going to be done by brokers, aggregating alerts, cross-matching in real time, using machine learning to classify, prioritization and follow-up, the TOMs. How do you optimize your resources? How do you communicate between all the different follow-up telescopes, not to repeat and get the most science out of what you're observing, and that this need to communicate very efficiently with all the rest of the ecosystem. And finally, with the data, we need new tools to do the physical interpretation. So you need models, interaction with theoreticians, you need new statistical tools to do inference. I don't know, use MCNC and other tools like this to get physical parameters. So let's go back to the alerts. So we've been talking about that the telescope, survey telescope, will produce lots of alerts. What are the alerts? Basically, triplets of images that contain the last image observed in a given night with a reference image from the same part of the sky and the difference image between these two after some image processing. And the alert also contains some metadata. For example, what is the flux in here? What is the position in the sky? What are the nearby objects, properties, etc., as much as you can. And as well as the history of detections. Was this object detected before? Was it not detected, perhaps? Up to which limiting magnitude, etc. And in the case of CTF, the Speaker Transfer Facility, we get about 300,000 alerts, packets per night, and about 15 minutes from the observation. In the case of LSST, we will get much more, about 10 million per night, and only 60 seconds from observation. And this will be different. We will get only the triplets of images with the metadata. And if you want to recover the history of detections or not detections of force photometry, you need to wait 24 hours. So this is what will dominate the landscape in the next decade, starting 2024. And this alert stream will be public. Everyone can access it, but they will have to access it through the brokers because of bandwidth limitation. So there was a competition to become broker, and 7 brokers were selected. I will show you later. So the idea is that the community will interact with alert stream through the brokers. So something very important is, as we are learning how to play with this new way of doing astronomy, is the interoperability. So going from survey to follow-up telescopes, there's a lot of things happening, and many of the brokers will be connected through alert streams, but also APIs with the community, with new visualization tools, new ways to interact with the data. And it's very important that all the elements are well connected and seamlessly connected. So I mentioned to you that there was this competition to become or call for becoming a community broker of LSST, of the Rubin Observatory. And recently, 7 different brokers were selected, 3 in the US, that, well, you have been having talks about these different brokers, 3 in Europe, and ALeRCE in Chile. So it's for us, it's great news, and we're taking this as a big opportunity for the local astronomical community, not only in Chile, but also in the entire region. So ALeRCE is a Chilean-led broker that was officially selected as one of the community brokers of the Galactic Observatory, and it's LSST. And you can find some of the papers, the 3 first papers in here: the presentation, the stamp classifier, and the LIneA classifier that I will discuss in a few minutes. So what are the scientific questions that we want to answer? First, what is the nature of transients, explosive events? Can we look at them at the very early stages so that we can understand the outermost layer, and with this understand their nature? Variable stars, can we react to new types of variability, microlensing, or perhaps stars that pulsate and change pulsation mode? Can we react rapidly to eclipsing events? Supermassive black holes, can we understand changing state agents? What about reverberation mapping and detection of intermediate mass black holes that vary in a faster time scale than more massive black holes? Tidal disruption events. And then, of course, asteroids. There will be many asteroids in the ALERCE stream. And this is an opportunity to detect near-Earth objects, understand the nature of the distribution of the asteroids in the solar system. So going now to the broker and its pipeline. What does ALeRCE do? So at the core of ALeRCE is the pipeline, and what the pipeline does is it receives the CDF stream, and the alerts are immediately stored in AWS. In this case, we're using AWS, and in parallel are cross-matched with public catalogs. In particular, it's the WISE catalog is very important for us. And then in parallel, we trigger 2 classifiers: the stamp classifier that is based on the image stamps, and a LIneA classifier that first needs to build the light curve with some pre-processing, calculating features, etc. And then the output of these 2 classifiers, as well as an outlier step, are sent as an ALeRCE output stream in something called Kafka, which is the format for the streaming that is used. And here you can see the execution times per alert. Typically, it's less than 1 second of CPU time per alert. And the elapsed time between the arrival of the alert and us finishing the classification. So it's usually times of seconds. And this is much faster, actually, than the time that CDF takes to send alerts, which is about 15 minutes. So at the moment, I think we can handle this kind of alert streams, and we have tested it with much larger alert streams, as I will show later. So this is a video that we did explaining more or less. So if you have a star in a galaxy, let's say a supernova, the telescope observed, alert is sent to the broker or the CDF group, and they generate the stream of alerts. We receive it with cross-match, store it in S3. We classify the image stamps. We prepare the light curve. And with this information, we can classify, and then we get output probabilities as well as other annotations. So here you see. Yeah, so you get many different astrophysical objects. So, and what we're doing is classifying the alert stream into a given taxonomy that we have discussed with the community, and the idea is that this taxonomy will be evolving with time. So we don't believe we can fix the taxonomy ever, because as we discover new phenomena and also the interest in the community changes with time, we will have to be changing this. But so far, this is the first version. We have transients and 4 types of supernova, stochastic events with different objects with disks that have vary stochastically, periodic objects either pulsating, eclipsing binaries, or in between objects, and of course real on both or both. So this classifier, as you can see, is a hierarchical classifier with first layer of transient, stochastic, periodic, and then secondary layers that go into more finer classification. And we could continue adding levels if we find that this is necessary. So you can access the data through a database, through APIs, through clients, through Explorer. And we have all of this for you to explore in the ALeRCE.science website. And basically the tables are divided between those that are like raw detections or non-detections, or quality environmental variables during the night. Some that are aggregated in time, and some that are aggregated in band and time. So object and cross-match information, for example. So image stamps. In the image stamps, we have divided them into 5 categories: active galactic nuclei, supernova, where you can see the host galaxy; variable stars, where you can see that usually you are surrounded by other stars; asteroids, where you see only in the science and in the difference, but not in the reference because it's a moving object; or both, problems with the detectors, or could be trailing satellites, etc. And also we have light curves that we can build as we aggregate data. So in the case of transients, all the supernova light curves, stochastics, different types of stochastic variability. These are the raw light curves. So this is for you to get an idea of what is the input. For example, in Valerisa, you see more variability. And then in periodic, that if you fold the light curve, you can see this kind of structure, the characteristic shape of our lyra, surface, etc. And in order to classify this, we need to build a training set. And this is basically what we do is we look at available catalogs of classified variable stars for supernova, for AGN, and then we cross-match with the CDF object table that we built. And this is the distribution of magnitudes for the transients, for the periodic, for the stochastic, all the labeled dataset in orange, and the unlabeled dataset in blue. So you see that the different classes have different distributions in magnitude. And so one thing that we do is we try to hide the magnitude from the classifier, not to be biased by the magnitude. And also this plot emphasizes as a very important difference between CDF and LSST, and that is the limited magnitude. With LSST, we need to go to 25 magnitude. It's going to be a huge challenge. Most of the available classified catalogs are in this part of the magnitudes, much nearby, something that you can observe spectroscopically, for example. So a big challenge for us is how do you move from here to here. And so the 2 classifiers that we have built are the following: the Standbased classifier, which is a convolutional neural network that receives as input these images, classifies the object into 5 categories, and this is the confusion matrix. So it's surprising how good this works with just the image stamp. And then the light curve classifier, this is a balanced hierarchical random forest by Paula Sanchez Saez. Well, these are 2021, sorry about the year. And what we do here is we do a final classification, but we wait also for a bit longer. We wait until you have at least 6 detections in a given band to do this classification, and so we can afford to have 15 classes, for example. And you can see the hierarchical nature of the classifier by these squares. And you can compare both, and you see that, for example, the STAMP classifier and the light curve classifier are quite consistent. Supernova are classified as supernova in here as well. AGN are consistent with these classes, and so on. And asteroids and bows have almost no cross matches with the light curve classifier. So a Standbased classifier is a convolutional neural network that receives the science, reference, and difference images into convolutional layers, and the images are rotated, enter the same convolutional layers, and then they're flattened and put together, taking the average of this, adding some metadata, and then finally you have the prediction. And this is the architecture. And the light curve classifier is based on feature engineering. So we design lots of features you can see in this site. more than 150 features per supernova. You define a taxonomy, and then we train using a balanced random forest. So we have tested more modern methods, recurrent neural networks, different things, and so far the thing that works the best, more robustly, is the balanced random forest. And in this balanced random forest, what you do is that every tree is trained with a balanced training set. So this is the trick that you need to do. Okay, so something important is that we have learned with this project and other projects before is the importance of not just trusting your confusion matrix. You need to go beyond that if you want to bring something from production into publication. I mean, sorry, something from publication into production. So, and I think this was highlighted by the COVID crisis recently, where there was this article in MIT where you see that there were hundreds of artificial intelligence tools and very few of them actually helped. And the problem is, as this is highlighted in the article, Frankenstein datasets, multiple sources with duplicates, tools developed by AI research will lack the medical expertise. I don't know. So this is the importance of working interdisciplinarily and the importance of validating results. So I think this is something. This is the bad result of the publish or perish culture that we have. So if you want to bring something to production, you need to go beyond. And what we have done is that we test these classifiers at least one step beyond, which is looking at the unlabeled set. So the unlabeled set is just everything that we get from CDF that is not labeled. And we do some basic tests. For example, this is the galactic distribution of the unlabeled set. And we see, okay, where are the agents in this diagram? Where are the supernovae? So they are both away from the galactic plane. That's good. Where are the variable stars? They are in the galactic plane. Good. Where are the asteroids? They are in the ecliptic. And where are the bubbles? They are in everywhere, and also mostly in problematic regions, like close to the horizon. For the light curve classifier, we also look at the distribution in galactic latitude, and we compare, for example, with the extinction and the colors. So we see, for example, that redder colors are found in near the galactic plane, which is good. And we see at the distribution of classes. Is this the distribution that we expect? Yes, we expect fewer supernovae than variable stars. So this is a good sign. It could have been that is completely the opposite. And this will tell you that there is a problem with your classifier beyond the training set. And the same with the light curve classifier. So you see the supernova classes are the less dominant, and type 1a supernova are the most common, which is what we also observe. Okay, so let's show you some tools. So the ALeRCE Explorer is in this address. You can quickly query for different objects. These are type 2 supernova, for example. I can look at the probabilities, look at the image stamps. This is designed with a lot of thinking behind. You can cross-match with different radius. You can, for example, see the net redshift. You can move between objects just with your keyboard in this list on the left. So it's designed to be very user-friendly, and we use it every day. Then the Supernova Hunter, which is a tool that we use to find the youngest supernova. So, for example, I can look at the supernova from the last 48 hours or whatever hours that you want. Look at each candidate and label it as a candidate, a real candidate, or I mean, a good candidate or not, perhaps a bogus. The Watchlist service, where this is something that came from the community as a requisite. For example, you have a set of positions in the sky that you are very interested, and you would like to be notified of any alert that coincides with that position. So we have built this service as well. You can create your watch list, adding with a CSV. Here's how you can, everything is explained. And for this list that contains the objects, for example, this object contains 6 matches in the last few days. And I can go and look at the light curve, and I can choose how often I want to be notified, etc. So really recommend you to start using these tools. Some other tool, we are integrating the CDF data release into ALeRCE. So, for example, I have this light curve based on the alerts, and if I compare it to the data release, I get many more points. So I get a better view of the light curve of this object. And we have found that this is particularly important if you want to detect outliers, because you really want to see the true light curve of the object, not just the light curve of changes above or below some reference. Yeah, okay, and some other impact that we have had is, for example, this single stamp classifier. The advantage that it has is that it's very fast, because you only need one detection. You can get a crude classification into the 5 classes I mentioned. And if you look at the distribution of time between first detection and last non-detection, and time between second detection and last non-detection, you would see that if you trigger follow-up with the first detection, you can get much younger supernova. So this histogram peaks in 1 day. But if you wait to the second detection, which is normally what we have been doing when you have a huge alert stream, you have to wait 3 days. So if you want to do follow-up in the first day with CDF, and with LSST will be worst, you need to be able to provide a quick classification with only one image. So these are examples. This supernova was first detected by CDF, and 4 hours later, we submitted a report to TNS. So something I didn't mention is that we are using machine learning to do the automatic classification, but we use the Supernova Handler every day to look for interesting candidates. We veto those that we don't trust, and then we submit to TNS manually. And because of this, there was a spectroscopic confirmation before the second CDF detection. Same thing here. First detection in the G band in CDF. 8 hours later, we submit a TNS report. We have a spectroscopic confirmation before the second CDF detection. So this will be more and more common with LSST, because the cadence of LSST is not as fast as that of CDF. We've been doing follow-up of interesting objects as well. So this is led by Alejandra Muñoz Arancibia and other people in the collaboration. We are collaborating with some Russian colleagues, where they have been providing 1 hour spectroscopic time with a 2.5 meter telescope, and we are getting spectral sequences with different telescopes. And this, in this case, is a supernova with a spectra observed 14 days before explosion. So we have a growing, very large community of users, and we have users in, if you look at the IP, where they came from, more than 125 countries. If you look at unique IPs, we have more than 6,000 users. We have been organizing workshops with other brokers like Think. We have get feedback. We organize getting feedback from the science collaborations. So we ask for the most requested products and services to the different science collaborations. And for example, this is where the Watchlist appeared. And so we decided to go for a Watchlist. And the community has been following up the objects that we submit to TNS. We have submitted about 1,500 supernova, and about 10% of them have been spectroscopically observed and confirmed. And you see here the distribution of classes. So mostly type 1a supernova, then type 2, and then other classes. And we have a bot in Twitter, ALeRCE Discover, that every time the supernova reported by ALeRCE is confirmed spectroscopically, you will see the notification. Some other results, more recent results. This is led by Paula Santos. She has been looking at changing state AGN in the CDF dataset, and she has been working with the variational recurrent autoencoders in different configurations to make sure, in order to detect outliers. And in particular, she's interested in changing state AGNs, like the ones you see here. So I really recommend you to look into this plot, into this paper. Some other results if we want to do inference in the huge alert stream that is coming, we cannot do MCMC. I mean, not for a big amount of objects. So one thing we have been playing is, and this work led by Alexis Sanchez in a paper recently accepted for the machine learning for physics session of the NeoRIPS conference, is using amortized variational inference to get fast posteriors. So the idea is that if you have a light curve, you can infer the parameters of a network that parameterize the full posterior. So with GPUs in milliseconds, you can get the posterior that normally would take hundreds of seconds per object in MCMC. And we are comparing MCMC with the amortized version, and this seems to work. So it's a potential solution to the inference, solve the inference problem with huge stream of data. Some other project that we have been working is the association of host galaxies. So all the objects that we have been submitting to DNS, we manually select the host galaxy using Aladdin with a Jupyter notebook that we send every day. We associate the galaxy. And with this, we have been building a training set to train a neural network to do the same task. So how we do this, we give an image at the center of the position of the transient, and then we tell the network to predict the position, the vector between the transient and the center of the host galaxy. And this is we call DeLight, deep learning identification of galaxy hosts in transients. And surprisingly, it's working even better than very, very small, slow methods like gradient ascent that can take hundreds of seconds as well. And with this, we can do 5,000 galaxies per second. So it's really fast once you have the data. So this is an example. This is the position of a transient, and this is the host galaxy. Probably the center is here. So if you just, what we do is we represent this in a hierarchical way in order to not confuse the network with too much data. More resolution in the center, less resolution outside. And with our method, we can correctly predict the position of the host. And using, for example, sex factor and looking at the ellipses, and with this deciding what is the host, the method gets confused with I don't know, some other part of the galaxy. Yeah, and here you can see the comparison. And inspired by this work, we also realized something that is quite important. This is an alert stamp triplet from CDF. This is about 60 arc seconds, 1 arc second pixel size. That's CDF. But this is the size of the LSST alert stamps. They're tiny. They're tiny in comparison. I mean, LSST is going deeper. The resolution is higher. It's 5 times higher. It's 0.2 arc seconds. But for those objects that you can do follow up, there might be not enough information to do a fast classification. So what we're trying to push is to change the way we represent image stamps in LSST. We want to push for a hierarchical representation of the alert stamps. And we are working now with the LSST pipeline team, trying to do some tests to see what are the benefits and disadvantages of this method. But we are convinced that this will solve lots of problems. And by doing this, you can also solve the host galaxy identification problem for free. And you can, if you use this for the PSF representation, you can also have a better characterization of the PSF in the tails beyond 3 arc seconds, because these alert stamps in SST are going to be 6 by 6 arc seconds, so 3 arc seconds from the center. These are examples from other alerts where you have satellites. That's going to be our nightmare in the future. And if you only use a very small image stamp, you wouldn't see that this was an asteroid. You wouldn't see that this was an object that moved and was rotating across the field of view. And these are other examples of supernova and bogus. So we are pushing for this to happen. So moving on, what is the team doing now? The team is working to unify the CDF information with ALeRCE. ALeRCE is a pair of telescopes that are located in Hawaii, smaller telescopes, so noisier data, but they have a very good cadence, and they are expanding they're putting a telescope in Chile and one in South Africa. Their main objective is to detect kind of city impact size type of asteroids, but they are getting also many supernova. So, and this is an example of combining the light curve from CDF in red and green with ALeRCE in orange and cyan, which are the filters they use. So you see there is a lot of complementarity. So we're collaborating with them, we're generating a new alert stream, and we're cross-matching in real time to make this available for the community next year. Moving on also into the future, this is the proposed infrastructure of ALeRCE for LSST. We have 3 layers: speed layer for real-time operations, the pipeline using Kubernetes and all these modern tools, working on the cloud, the offline layer, batch layer, where we can do massive processing. So ask a question to the data set, but you need to use Spark, Slurm, like massive data processing tools. And then the serving layer, where you can provide a front end or Jupyter Hub for the community to play with the data, like the Vera Rubin science platform. We have been doing tests of ingestion of alerts at a similar rate of LSST, and we can do it with Kafka. We can do the processing with Kubernetes. We can do enough insertions and spatial queries that are beyond what LSST will require. So we are confident that we can do this, but it's going to be a lot of work and will require a lot of people. And with this, I finish. So just to summarize, we have the light curve classifier with 15 classes, more than 2 million now, I think, classifications. We have tools like the Explorer, the Jupyter Notebooks, the ALeRCE Watchlist, the Supernova Handler. We have a modular pipeline design, and we are preparing for Rubin. And something I didn't mention is that also, that is shown here, is that we have made a huge effort to build science case notebooks for people to start easily into using the ALeRCE tools. So really, you're invited to look at them. If you find anything that you would like to include, please let us know. We want to hear from our user community. So that's it. Thank you very much.
Thank you very much, Francisco, for the very interesting talk. Now we have some time for questions. If you joined us on YouTube, you can put your questions in the comment section, and I will redirect them to Francisco. And if you joined us here on Zoom, you can ask it yourself. Luis, you have a question? Go ahead.
Yeah. Hi, Francisco. Well, first of all, congratulations. Beautiful work. I was wondering, I think we met in Tucson some 5 or 6 years ago.
Yes.
How long did it take to build all of this? And how many FTEs you have there?
Good question. Yeah. So something I didn't mention is that we started building the interdisciplinary group before ALeRCE began in something called the HITS project, which was about finding supernova in real time with Deca. So this took, I would say, 4 years for the interdisciplinary team to know each other, know how to talk to each other, and start doing something beyond what we would do by ourselves. Mm-hmm. After this project, we realized that.
When was that? When was that, Francisco? When did it start?
2013, 14, okay. 15. This was okay. when we ran so we started 2012 when we identified the problem. 2013, 14, 15, we actually did the experiment. We analyzed the data until 2018. And in 2017, we realized that we were one step from becoming a broker. We just had to repeat what we had done, but only the last step and more massively. And also, this will not be an experiment anymore. This will be like a production system service. So this will require full-time engineers. And since 2019, we started hiring full-time engineers dedicated fully to ALeRCE. and the size of the team has been varying. You know, the market is quite dynamic now, but we have been up to 6. We have up to 6 full-time engineers, plus minus, I mean, or minus 2, let's say, sometimes, and with different backgrounds. But I think the key people now in the team are the data engineers that do build these services. It's not me, it's the engineers. So we
I know, but you've been able to bridge the two
Exactly.
groups. That's a challenge by itself.
Yeah, and funding is also an issue. It's very difficult to get this kind of funding from academic funding tools.
And who funds that? The government, the ministry, or the university, or a combination?
It's the government, but through different institutions. So different institutions see the potential, the importance of this project, and we build a collaboration. And at this moment, there are 3 key institutions: the Center for Mathematical Modeling at the University of Chile, the Millennium Institute of Astrophysics, which is a 10-year project, and now the Data Observatory.
Wow. Francisco, congratulations. It's really beautiful stuff. Okay.
Thank you very much.
Thank you, Luis. Julio Camargo posted a question. Do you intend to obtain light curves or periods also for asteroids?
Yes, actually, that's something you can actually do, and we have a notebook that does it, but we haven't designed a web interface for that. So in our database, we have a table of everything that is classified as asteroid by the MPC. And we also have our own stand classifier probabilities. So you can actually find asteroids that are not in the MPC. And using the detection table and the object table and the asteroid table, you can actually build the light curve. We have some students doing this. Yeah, but if you think that we should build a tool for this, we might consider it.
Okay, thank you. While we wait for more questions, I actually have a question, a curiosity. Since determined periods it's not something that it's a simple problem of convergence to get to the result. You usually have to test a lot of unknown periods until you find it. Do you have any type? I don't know if it is even possible, but do you have any type of machine learning for that, or do you do in the traditional way using PDM?
Yeah. So yeah, we don't. We have. There are some students that have tried some things, but so far we're using traditional methods like that because it needs to be very fast, like analysis of variance. And of course, we can try different methods. Like there's a library some people in our group built. It's called P4J that has different methods, traditional and using more modern, like using mutual information. And for example, we know that there is a problem with the periods of eclipsing binaries, which is a common problem for very basic methods. Yeah, so that's something we are working now. There's Marcio Catalan, maybe you know, that he's very interested into this. And yeah, some students are looking on how to do this. But the real problem is, how do you do this super fast? You don't have a lot of time per object. So we need to rethink, I think, all the tools that we use, aiming at the milliseconds for LSST. It's going to be very challenging. If machine learning can do it, that would be amazing. Yeah.
Yeah, it's a very difficult question to answer.
Yeah.
I've worked with some of this type of problems, and one method that is fast but probably not fast enough for the case of eclipsing binaries will be the BLS, or the box fitting list squares. But it probably wouldn't be fast enough. So, well, thank you, Francisco. More questions?
Yeah, but just a quick one. I mean, you're already using Tom to.
Yeah, we're connected to the Tom. Yeah.
Okay.
So we have.
So it's a successful experience.
Yeah, I mean, we started at the beginning of the pandemic, so it was a bit bumpy at the start, because the observatories were closed, and we got some time to experiment with these tools, and we send hundreds of observations. It's the future. We need to connect to them. Yeah.
Mm-hmm. And that's what Gemini, SAR, all of them.
Yeah, well, the LC OGT, and I think SOAR is also, but we were only using one of the LC OGT telescopes for that.
Okay. Okay.
The 1 meter telescope. And also say that if you are interested in collaborating with us, I mean, developing tools some things that you may need. I mean,
oh, we definitely are, but we're gonna take this offline.
Yeah, and
We'll chat that. You know that I want to collaborate with you guys.
Yes, yes.
Why do you think we invited you? There is always a catch. I'm joking. I'm joking. I'm joking.
Okay. More questions? Okay, if there are no more questions, we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. And for the next week's webinar, we will have joining us Troy Ryan from the University of Pittsburgh, continuing in our series of LSST brokers, and he will be talking about the Pitt-Google Astronomical Alert Broker. Thank you everyone for attending, and a special thanks to Francisco. Thank you, Francisco.
Thank you for the invitation.
And well, everyone have a great day, stay safe, and I hope to see you all again next week. Thank you.